And a very good afternoon to all our viewers. My name is Mahendran Reddy. I'm the head of Ecosystem of Additive Manufacturing Innovation Cluster, formerly known as NAMIC. It is with greatest excitement and pleasure that I welcome all of you to our NAMIC Virtual Summit, staying ahead of the curve with AM for the transport industry. At our recent NAMIC Virtual Summit for the built environment, where we invited experts from all over the world to explore contemporary issues and future-cast ideas for the construction industry, it was really well received. And for those of you who have missed it, you may find the playback on our YouTube channel by looking up NAMIC Singapore on our platform. So here with us today are a diverse and a global mix of speakers from the United States, Europe, and of course, Singapore itself. These speakers will be deep diving into the automotive and land transport industry, where the potential of additive manufacturing leaves much to be explored. Traditionally, additive manufacturing has been mainly used for rapid prototyping for automotive vehicles, but in recent years, advances in the technology and digitalization has enabled additive manufacturing to transform the ways in which end-use parts are designed, manufactured, and even distributed. In fact, it was revealed in SmarTech analysis report that by 2029, automotive 3D printing would have generated $9 billion in revenue for the production of end-use parts alone, compared to $1.39 billion in 2019. So what opportunities and developments can we foresee happening in the land transport sector in the next decade, aided by technological advancements that include AM as well? We shall leave this question to be answered by our speakers, whom I'm sure are all eager to share their perspectives with all of us today. So before we begin the summit proper, let's take a look at the agenda for the day. Kicking off the session is a welcome address for NAMIC's Managing Director, Dr. Chaw. Next up, our keynote speaker, Mr. Helge Schneevogt, will set the stage by providing perspectives from Mobility Goes Additives, a global AM network based in Berlin, Germany. Following which we have presentations from Janis, Kretz, Daniel Kluth, John Su, Stefan Roeding, and Jonathan Meyer. As adapters and innovators of AM, their sharing will give you a comprehensive overview of AM adoption in the transport industry. So after we hear from all of these speakers, we will be then joining we'll be opening the floor to the audience with a live panel and Q&A session. So do remember to leave all your questions by clicking the Q&A button below on your screen. And joining them and to facilitate this session, we are pleased to have with us Joris, who is the Vice President of Consulting of SmarTech Analysis, which delivers industry analysis, data, and market forecasts for the 3D printing industry. Joris also provides multinationals and startups with strategic advice and does technical due diligence for investors in the 3D printing space. So before we get started, Joris, would you like to say a few words to our audience today?
Yeah, of course. So first off, Mahendran, thank you so much for having me. Thank you for doing this again. And yeah, it's a very exciting time, especially for transport right now, because we're going from it being a prototyping technology for several big, large automotive firms, making tens of thousands of end-use parts in more and more normal cars. Right? It used to be in F1, it used to be in like hypercars, but now we're seeing mass customized solutions in just regular cars that you could buy, and that's very, very exciting. I think to see mass customization, end-use parts, things like parking sensors, and more normal parts being made for consumers. So we're going into part volume. We're going from several thousand parts to hundreds of thousands of end-use parts. So it's a very, very exciting time right now for 3D printing and automotive.
All right, thanks, Joris. We're gonna get back to you soon with all our speakers right at the end of the session. So hang in there, listen to all of their conversations, and we'll pull all the questions together with our audience as well. So thanks for that introduction, and let us begin with a welcome address by Dr. Chaw, who is the Managing Director of NAMIC. NAMIC is a Singapore government platform initiative to catalyze innovation and scale industrial adoption of digital additive manufacturing technologies. Since its inception in late 2015, NAMIC has raised millions in public-private funding to catalyze various AM initiatives across several industry sectors. Before joining the public sector, he spent several years with HP Singapore and Chartered Semiconductor Manufacturing, where Dr. Ho undertook various executive roles in technology and product development, as well as supply chain manufacturing operations. He's also an advocate for technology for good and 3D printing's role in sustainable development and manufacturing. So let's welcome Dr. Chaw, please.
Thank you, Mahendran. Very good afternoon and morning and evening to everyone. First and foremost, I'd like to extend my warmest welcome to everyone who's taking precious time to attend this virtual summit. This, I think, is our second one officially on a sector deep dive. And we've picked the land transport and automotive industry, given there's a lot of progress and innovations that's happening in this space. And today, I think we have 7 distinguished speakers and of course, our partner from SmarTech Consulting, who has taken time to be with us to share progress and their views of how additive manufacturing driven innovations will drive the transformation of urban mobility for the future. They represent some of the global leading automotive, land transport, and AM design material fabrication specialists, and I'm not going to reel off the names, but we've selected some of the leading organizations from the US, from Germany, from Singapore, and even from Korea as well. The automotive industry has in some ways been one of the pioneers in adapting additive manufacturing since decades ago. With fast technology development and availability of new materials, the applications utilized by car makers actually have evolved rapidly. And in this aspect, NAMIC actually has been in some ways leading the industry sector specific deep dives and engagements with companies across the additive manufacturing value chain in Singapore to enable industrial adoption. And that includes the development of AM technology platforms. And the insights we have drawn from these engagement adoption initiatives have pretty much driven the economic agency's effort and engagement in order to attract the AM technology providers, as well as to guide our local research and development performed by our public sector research performance in universities and research institutes. When we first started more than 5 years ago, we only have the MRT, which is the mass rapid transport trains, and automotive aftermarket industry. Today, we are very proud that Hyundai Motor Group has committed massive investment to build an electric vehicle manufacturing plant at the Jurong Innovation District in Singapore, which will produce 30,000 vehicles by 2025. And this is something that was in some ways unthinkable several years ago, but we believe that technologies such as additive manufacturing will play a very big role in this new emerging space for us. Under Singapore's latest Research Innovation Enterprise plan, or RIE 2025 for short, I just wanted to share that sustainable manufacturing is a key focus, and NAMIC will continue to operationalize Singapore's additive manufacturing plans as the national accelerator in order to catalyze industrialization of technology for the industries. And on this point, pivoting to digital transformation, smart factories, by adopting automation and digital manufacturing is extremely crucial towards fulfilling and transforming Singapore's manufacturing industries. So to deepen the manufacturing capabilities, cross-domain technologies such as artificial intelligence, automation, additive manufacturing, of course, will enhance our manufacturing hub value proposition and strengthen its supply chain, our supply chain resilience. We'll continue to build upon the R&D investment under the remit of the Research Innovation Enterprise roadmaps to continue to drive for technology adoption and innovation. And this will include sustained investments in our public sector in research and development capabilities, as well as supporting our companies, whether it's multinationals or small, medium enterprises, that are keen to embark on this transformation process. With that, I just want to once again send my thanks to all our distinguished speakers, especially those from the US. Very much appreciated that you're staying up late for this event. I hope all of you will have a very fruitful and productive session today. And thank you very much for your attention. Over and back to you, Mahendran.
Thank you, Joris. Thanks very much. Now it's my pleasure to invite our keynote speaker, Mr. Helge Schneevogt, to share with us on Less is More, Sustainable Transport through AM. Helge is the project manager for technology and sustainability at Mobility Goes Additive, a leading global network for industrial additive manufacturing in Germany. He's also an expert in applied 3D printing and ecological sustainability in AM, especially in the field of recycled materials and bioplastics. As a trained transportation engineer, his main interest is in the field of mobility and traffic engineering, his specialty and passion being railroads. In addition to supporting various working groups within the network, he analyzes trends and developments in the AM industry, especially with regards to their sustainability. In line with this, he has prepared a sharing on achieving sustainability with AM in the transport sector. So now let's hear from him. Helge, guten Morgen, and over to you, sir.
Thank you, Mahendran, for this warm welcome. My name is Helge Schneevogt. I'm project manager at MGA, Additive Manufacturing Network. And the topic of today's keynote, which I will hold, is Less is More, Sustainable Transport through AM. At the moment, we're coming out of a dark tunnel named coronavirus. And what we see on the horizon is a bright light. And this bright light symbolizes two things. One is the regained hope and optimism and the growing business numbers. But the other side of this is new challenges. One of these new challenges is climate change. The devastating effect of this climate change could we have seen in the southwest of Germany with the devastating floods there, costing 180 lives. We all agreed, or most of the countries agreed, to limit global warming to a goal of 1.5 degrees in raise. But this doesn't come on its own. We have to take action. And to take this, ecological sustainability is the key lever to achieve this. So we thought about the most economical way of transport. Well, this could be one, but maybe not for all of us. I'm just joking. I'm speaking about rail transport. And rail transport considers itself as one of the most sustainable modes of transport, or the most sustainable one. And a strong rail is needed to reach our climate goals we all agreed on. Railway transport can substitute flights, short-haul flights and long-haul car trips. But to realize this and gain more customers, an increased attractiveness is needed of the railway mode. This is mainly done by a better availability of vehicles and infrastructure, and this is where additive manufacturing comes into play. Additive manufacturing can lead to the reach of optimal availability of infrastructure and rolling stock. Moreover, AM can lead to a shortening of MTTR cycles, mean time to repair, and an optimization of supply chain cost. And as well, AM can do an improvement in ecological sustainability. But what exactly can be done with AM in the railway sector? Here are some examples. As I've just said, AM can lead to a higher availability of parts, spare parts mainly. Also, partial substitutes can be done in obsolete solutions. Functional integrations and productions from lot size 1 are also benefits with AM. Saving manufacturing costs and individual solutions and also bionic design potentials are ideally done with the use of additive manufactured parts. But let's have a look at our current material economy. This linear economy is in nearly all countries in the world the status quo. We start with a material input, which then gets produced into goods. These goods get then distributed, used, and disposed at the end of their service life. And waste and emission leakage occurs in the form of CO2 and other harmful emissions, which lead to global warming and climate change. So what is the answer to this not very sustainable material economy? It is a circular economy, a circular approach. The circular approach means reusing goods at the end of their service life, which are perfectly usable but not needed at their place anymore. It also means remanufacturing and refurbishing goods which are slightly worn down but can be remanufactured and refurbished. And it also means at the end of their service life, harness valuable resources and produce something new out of these. Also, a longer use of goods which are perfectly usable is meant with a circular economy approach. Another illustration of the circular economy approach can be here in a circle. It's the exact same steps, named slightly differently. And here we can see where AM can be used to support all these steps. So with additive manufacturing, lighter parts can be produced in the design phase with less material used. An on-demand production can be done ideally with AM in the production phase. Also, digital warehousing eliminates the physical storage of spare parts which might not be needed. Also, a localized production, for example, in Germany, could be done ideally with AM, and parts don't need to be shipped around the whole world. In the use phase, an extended use and additive repair can be ideally done with additive manufacturing. And in the collection phase, material marking with additive manufacturing supports this and supports the recycling phase, where recycled materials can be used to minimize the use of virgin materials. And this all has very large ecological effects. But how do you use all these levers which are offered by the use of additive manufacturing? You need a strong network over the whole value-added chain of additive manufacturing, like MGA is. And we, together with all our members and partners, are realizing all these potentials, or are helping to realize them. We at MGA are organized in different working groups where we do in-depth looks at several specific topics. One of our working groups is the Ecological Sustainability Working Group, which I'm responsible of. And in this very working group, we mainly have 3 pillars. For example, life cycle assessments, where we deeply assess products and their whole life cycle regarding their carbon footprint. Also, we introduce external studies with partners to gain more insights on the ecological effects. Also, we collect best practice use cases to learn from one another. But not also MGA has seen the big issue with sustainability. Also, one of our biggest member companies, Deutsche Bahn, have seen this quite some years ago, and they launched their Das ist Grün, This is Green campaign, where they collect many over 100 use cases of green projects. But also, they have seen the advantages of additive manufacturing very early. In 2015, they started with 10 additively manufactured spare parts. And now at 2021, we're at over 25,000 additively manufactured parts, which don't only need to ecological or sustainable effects, but also to monetary effects in the form of 1.2 million euros. One example of these additively manufactured spare parts is this secondary roll stop built into an ICE high-speed train. It can be seen here, and it stops the rolling motion in the curves the train is traveling around, so it limits these, but the part doesn't get worn down regularly, so it isn't available as spare part. This got nevertheless damaged in an accident and put the whole train out of service. And then AM could help to remanufacture this part in a WAM process and put the car back into service in record time. Another example of additive manufacturing within Deutsche Bahn and the cooperation of MGA is this DB cargo hinge. It's a hinge built into a cargo wagon, and one of our working groups, the working group Market Needs, did an extensive topology optimization to save material and production costs. And what we did, moreover, was an eco calculation of this very part and this optimization. So what you can see here in this left figure is the comparison of 3 different manufacturing processes. You can see the part weight of the original part, which is a cast part, a milled part, and an AM part, which was manufactured in an LPBF process. Through the topology optimization, half the weight of the part and half the material could be saved by keeping all the strength the part has in its original design. Looking at the production waste, we see especially the milling comes with a huge plus of over 500% of the original part, because it has to be milled out of a billet, and most of the billet gets milled into chips, which are then waste. In comparison, the additively manufactured part only has little supports and could reduce this production waste compared to the runners of the original cast part by 76%. Now we look at the bound energy in the part and the CO2 emissions. Here on the left figure, you see the total energy of material and process in comparison of these 3 manufacturing processes. You have to keep in mind that per kilogram, the bound energy in the raw material of additive manufacturing powder is way higher than per kilogram cast iron or a mill billet or just a billet to get milled. But through the topology optimization and the material savings, the total energy could be reduced by about 11% compared to the original cast part. And with this comes the minimization corresponding of the CO2 emissions and the carbon footprint. But nevertheless, we have some to-dos for the industry. We have seen some great ecological examples, but there are still some points open. So an AM production with green energy is needed, in our opinion, as most of the energy used is electric energy and could be easily replaced with green power. Also, life cycle assessments are needed to assess the whole ecological footprint of certain products and to allow for the decision for the most sustainable alternative. Also, generic carbon footprints calculations are needed. We also need transparency over the whole value added chain, or an increased transparency. It's quite transparent at the moment already. And more recycled and bio-based high performance materials are also needed, in our opinion. So let's wrap this up. Additive manufacturing is a key enabler for improved railway maintenance. It is a perfect fit for the circular economy, and it allows for a competitive carbon footprint by material savings. But yet, the full green potentials yet need to be leveraged. And if we do all these tasks I've just shown you, we really drive into a bright future and don't see so many challenges ahead. Thank you very much.
Helge, thank you very much for that optimistic vision for the future, despite all the challenges that do lie ahead for us. And so just a gentle reminder to our audience today. So please post all your questions on the Q&A tab that you see on the bottom of your screen. and not to put it on the chat function. So this will enable us to pick out your questions and aggregate it at the end of the session to be raised during the panel discussion. So next up, we have a pair of specialists from Daimler Truck AG, Janis, Kretz, and Daniel Kluth. The two of them will be doing a joint presentation on an investment into the future for businesses with 3D printing. So a quick introduction of Janis. He's the digital supply chain manager for 3D printing in the Center of Competence 3D Printing at Daimler Buses. In his role, he's responsible for decentralized production and digital rights management. Prior to his present role, Janis studied at the Neue Universität of Applied Sciences, graduating with a Bachelor of Engineering and majoring in production management. And later he worked on a 3D printing project under customer service and parts at Evo Bus, where he presented visionary business models in AM. So together with Janis, we also have Daniel. After successful further training as an industrial specialist at IHK Akademie Schwaben, Daniel has been awarded the Bachelor of Professional Management for Industry. Currently, he holds the role of procurement manager and category buyer for additively manufactured non-metal parts in the Center of Competence 3D Printing at Daimler Buses. Besides AM parts, Daniel also works as a buyer and scheduler for various spare part commodities. So now that we've gotten to know them a little bit better, let's hear what they have to share. Janis and Daniel, over to you.
Yeah, thanks, Mahendran, for this very warm introduction. I will just share my slides for you. So I hope it's good to see for everybody. Yeah, hello to you all. Hello and a very warm welcome to the audience from our side, from the Daimler Buses side. It's a pleasure for us to be invited here today and to show you a little insight of our 3D printing activities. Yeah, as briefly told, my name is Daniel Kluth and I'm working as a procurement and logistics manager for 3D printed parts within our Center of Competence 3D Printing here at Daimler Buses in New-Ulm in Germany.
Thanks, Daniel. Also a warm welcome from my side. My name is Janis Kretz and I'm the digital supply chain manager of our Center of Competence. So I'm responsible for the topic of a decentralized production, and I'm focusing on new digital business models that are possible with 3D printing. But I will give you some more insights about these topics later on.
Yeah, thanks, Janis. Today, we two together, we want to show you why 3D printing is an investment into the future of businesses. Daimler Buses itself is a legal entity of the Daimler Truck AG, and within that, we stand for about 20,000 sold units and add a revenue of about 2.7 billion euros to the Daimler Truck AG. The most important brands in Europe are Mercedes-Benz, etc. And for India, it's Bharat-Benz. Now, so one of the central question is, why should companies use 3D printing in their very own businesses? Well, there are a few motivations for that. One topic is the possibility to save a certain amount of costs due to the loss of tooling, for example, or the avoidance of stock in the warehouse, which is also need to be financed, of course. But also you can create a bigger customer satisfaction by better delivery performance, like creating shortened lead times, and also individualization is becoming more and more a topic with the possibilities of 3D printing. Considering these motivations, we started a cross-functional project team with the order from our board of management to analyze potentials and possibilities of 3D printing up to the elaboration of a very new business model. Today, we're more than 25 colleagues with different areas of expertise. We are rating the possibilities of 3D printing, like new technologies and of course materials, but our main topic is to bring 3D printing from the prototype world to the serious world with safe processes and, of course, reproducible quality, which is very important for our business. Our overall strategy, therefore, is to build a completely new business model with additive manufacturing. We start with the implementation of first quick wins, for example, avoiding costs of parts and toolings or speeding up lead times. And after that, we scale up this model to other units and new business areas. And in the end, we're building up a whole new business model. For all these tasks, we founded in 2019 our Center of Competence, 3D Printing, with 4 main agile Scrum teams in the field of business development, quality management, product management, and digital supply chain. One of our first steps was to analyze the total volume of spare part numbers of about 320,000 part numbers. Out of them, we have about 120 parts on stock ready for a delivery to our customers. But the most problems, and of course the biggest potential, offers our around 200,000 part numbers which are ready to order for a customer, but they are not on stock right now. They will be only ordered for a customer when there is a special need, or even they are connected to some special customers, for example. And this often leads to long lead times and needs efforts in tooling, for example. But we do not only work on very operative topics. One of our main tasks is also to coordinate all 3D printing activities within our entities and to use all the synergies of our project team. Now, by these methods, we already implemented more than 400 different bus parts. They are ready to sell and ship to customers, and more than 800 printing data sets in our digital warehouse. But we also focus on further potential, like, for example, prototype parts and customer special requested parts, which are parts that only are designed and manufactured for some special customers and their very own buses.
So thanks very much, Daniel, for your introduction. So in addition to all of these points, we have already implemented 3D printing, and especially the data on which 3D printing builds on offers the way to completely new business models. And here we see the vision or the chance for fundamental change of the previous business model from a physical business model to a digital one, or rather the shift from a physical warehousing to a digital storage. Yes, but what does this mean in concrete terms? Due to the continuous expansion of our digital storage and the provision of the necessary database, we already laying the foundation for such a digital business model as our big picture for the future, with which we at Daimler Trucks already want to start in this year. So in addition to our traditional after-sales core business, the selling of physical spare parts, we want to supplement our portfolio by selling digital services in form of encrypted 3D printing data and 3D printing licenses. And here we move into a completely new business area, and a lot of different requirements have to be fulfilled. For example, the setup of a secure data transfer, as well as the setup of a digital rights management, to ensure that an encrypted 3D printing file can only be used and produced in a limited amount of parts. And in this context, we already made a partner selection for the license management. And at the moment, we are in close collaboration with our internal IT department at Daimler to integrate this software solution for the license management into our current IT landscape. And with this technology for the license management, we are already laying the foundation and creating the conditions for a decentralized production. So the possibility to produce the part directly at the point of sale. But what does this mean in concrete terms? With a decentralized production, it will be possible that if a customer urgently needs a spare part, we will no longer have to send a physical part around the world, but only send the encrypted 3D printing data from our digital storage within a few seconds from one place in the world to another place in the world, and then to produce the part directly at the point of sale, for example, in a 3D printing hub or by certified service providers. And this ultimately leads to a significant shortening of the supply chain, and it has also very positive aspects on the environment. And in this context, we are focusing on building up a decentralized production network. And here on the one hand, we're in close coordination with our internal Daimler locations and subsidiaries. But on the other hand, we're highly interested in external partnerships, of course. And yeah, especially the market Singapore and the Asian region is very interesting for us as Daimler Trucks. So to set up and to roll out a decentralized production also in Singapore and in the Asian region. And with the possibility to produce the parts on site and on demand, 3D printing offers also a big step towards more sustainability and thus for the environment. So the setup of our digital storage and the possibility to produce the parts directly on site, for example, in Singapore, is accompanied with a big range of different advantages, like you see here on this screen. So by only producing the amount of parts that are really needed, 3D printing adds an important contribution to the protection of resources and for the reduction of material scrap. Other key benefits are, for example, the reduction of warehousing and scrapping costs, significant shortening of the supply chain, as well as improving the ecological footprint for the production of our spare parts. Yes, and at the bottom line, in our opinion, these environmental aspects are one of the key benefits of 3D printing. And this topic will also given special attention at the media at the moment. Yes, and now already coming to the final slide of our presentation. As a result for us, Daimler Truck AG, 3D printing is clearly an investment in the future of our company. And here you can see by means of a few keywords why this topic is so important for us. Yes, I hope Daniel and I could convince you in the last 15 minutes that 3D printing is very an economical technology, especially in terms of full costs, and that it's a very flexible and fast technology. And yeah, at the bottom line, like already mentioned, it's also very eco-friendly, where the positive aspects clearly outweigh. Yes, and now I hope we could give you a good overview of our current 3D printing activities at Daimler Truck AG. And yeah, I hope you could enjoy our presentation, and if there are any questions, feel free to ask afterwards in our panel discussion. So yeah, thanks very much for your attention.
Thanks.
Thank you very much, Janis. Thank you, Daniel, as well. Thanks to both of you. I'm sure our audience are very excited to find out all these digital manufacturing, distributed manufacturing that you've been talking about. I'm sure there'll be a lot more engagements after this presentation. All right, next up, we have Mr. John Su, Vice President and Founding Director of New Horizons Studio, which is a new unit of Hyundai Motor Group, which focuses on the development of ultimate mobility solutions. And so this New Horizons Studio is expected to push the extreme limits of vehicle development, building vehicles to traverse off-road terrains with unprecedented mobility through a combination of robotics and wheeled locomotion technology. With New Horizons Studio exploring new frontiers and innovations, John would be sharing about their exciting developments of ultimate mobility devices to provide new mobility solutions. And now I'll just hand over the time to John. John, welcome.
Thank you. Thank you, everybody. Thank you for this opportunity to speak about my work at Hyundai Motor Group. And I also want to thank the organizers of NAMIC for this opportunity to speak with you today, as well as joining the panel session later on. Hello, my name is John Suh, and I have the privilege of serving as the head of New Horizon Studio. We are a team dedicated to the building of ultimate mobility vehicles, or really about reimagining what is a vehicle. But before I begin, I want to just describe where my team fits into the larger context of Hyundai Motor Group, which is a very large company and well, conglomerate that is, and it's headquartered in Seoul, South Korea. It's best known for its three automotive brands, Kia, Hyundai, and Genesis. Altogether, it puts it within the top 5 of auto manufacturers by volume. The long-term strategy of Hyundai Motor Group is to change from an automotive-centric conglomerate to one about providing smart mobility solutions. This was announced about a year or year and a half ago. And to carry out this mission, it's really the job of the R&D organizations within the group to look at a range of different things shown here on this slide. Where my team fits in is in developing these new mobility platforms. And as it was noted at the top of this session, looking at electric aircraft, or you might have heard about our interest in robotics or purpose-built vehicles. That is, other parts of the company are doing that. My team is focused on what we call ultimate mobility vehicles, which is the subject of this presentation. Where I want to begin is how we did begin. It really began with a simple question, and that was, what if a car had legs and could walk? And when we asked that question, it really just spurs on other questions like who would benefit, where would it be useful, how would it work, what are the enabling technologies, and really what can we learn from them from the past, or even far past or even recent past. And one of the things that we realized was that the idea or interest of having vehicles that have legged locomotion has actually been in the minds of humanity, probably dating back almost at least 2,500 years ago for quite some time. But more recently, we looked at, well, in what situations would it be useful? Because cars are very capable. And the short answer is legs are needed when the car gets stuck, right? And the car can get stuck for different reasons, as shown in these slides. Sometimes it's due to very, very extreme events, earthquakes, flooding, landslide, heavy snow, ice, etc. But sometimes it can be, honestly, just driving in a place that you didn't expect to get stuck, and even very capable off-road vehicles can get stuck in a pothole that is bigger than what it appears to be, can get stuck in sand that does not appear to be troublesome to drive through, or driving over some snow, right, that doesn't look like a big deal, but it does end up holding up the car, right? So there are actually many situations where even capable four-wheel drive vehicles do get stuck. And so that led us to do a project that thought about, so what should this vehicle look like? What are some of the design principles that led to a project called the Cars with Legs project, for lack of a better name. We brainstormed all kinds of concept technologies. We made decisions on what the general vehicle design would look like. And one of the things we really want to focus on was that this vehicle should look like a car when it is, capable of working on a surface that allows for rolling traction. But in the cases where the terrain becomes too difficult, as shown here in a disaster environment, then the legs allow the car to continue traveling. And so certainly in times when disaster strikes and the road is washed out or obscured, then legs become really important. In the top of my talk about reimagining vehicle design, and this, among other things, really opens up from a fresh start what a vehicle could be. And one of the things we want to incorporate this idea called universal design. And what is universal design? It's basically an idea that says that what is a maximum audience or the maximum user base that you could design for. And in this case, I'm trying to depict the idea that we are designing for people who need to use wheelchairs for one reason or the other. And so this vehicle, it is designed from the beginning to accommodate a wheelchair. And so the ingress, egress, the doors, etc., we want to think about that and include that into our design. The other thing that we recognize is that, okay, in an urban setting, do you really need legs, right? Because roads are quite good, so is that really needed? So we recognize that, well, you're right. Okay, off-road is probably going to be the kind of environment where this capability really makes sense. Now, I could argue that urban settings, there is a role to play, but that said, truthfully, the off-road environment is a easier to sort of discern the utility. And so we looked at a lot of off-road applications, and we really have centered that or thought about off-road as the key area. And that's what you might have seen in 2019. We released the Elevate concept. It is designed to spend most of the time off-road, but it is fully capable of driving on the road. We have the legs shown here kind of almost fully extended, and that really provides a lot of advantages. First of all, it allows the vehicle to travel over obstacles of different types. The second thing is that even if the legs are not going over an obstacle like rocks, for instance, the legs function as an active long-range travel suspension, and that can keep the cabin level in uneven terrain, which could be useful for passengers or could be useful for cargo or scientific instrumentation. Now, moving on to design. So we said, okay, now we have a good idea of what the vehicle could do and where it should work. We began putting together a model. This is a 1/8 scale model of what the full-size vehicle could be. This is where we began looking into additive manufacturing, obviously for prototyping purposes, but we really understood that lightweighting, the use of either additive metal or additive composite plastics would be really important. So this particular model was used to design the walking gates, but was also our first look into additive. And from this sort of little model, that really opened up our eyes as, it doesn't have to be passenger vehicle scale. Maybe these smaller scale vehicles could be another area that we should pursue. And that's what we've been looking at also recently. And so what you have here in this picture is called Tiger X1. It is a small scale robotic vehicle built upon the same principles as Elevate. It is for carrying packages, goods, or in this case, sort of sensor instrumentation to do remote monitoring and survey work, but it could be configured to carry cargo as well. As we continue in this journey to reimagine vehicle design, we thought about, well, if this vehicle is going to be operating in remote areas, then we ought to have perhaps the ability to lift and carry this vehicle, Tiger in this case, into remote areas. And so here, this picture depicts Tiger being carried by a electric UAV or perhaps a VTOL aircraft. And then once we said the possible requirement to be airlift, then weight became a very, very important factor. Now, weight is important for automotive in general, right? But perhaps not essential. But in this case, it becomes essential because then your ability to be airlifted is a function on how heavy it is, right? And that led to looking at more additive. In this case, carbon fiber, or other plastics, again, prototype in nature, if you will. However, that said, we really looked at how might we build a majority of the components or as many of the components, even at the prototyping scale with additive, right? Because then that would be a way to explore what's the longer term potential for production if we were to get there. Once we get to this step, right, that opens up even more questions. It's like, well, what is the nature of the plastics that we're working at, and carbon fiber being one of them, and that opened up even more questions like, well, okay, carbon fiber is an incredibly high performance material, but it has a recyclability problem, right, as was sort of mentioned earlier. And so then we began looking at other materials. Fortunately, and the good news is so far is that there is an effort to make things more sustainable, among them bioresins, right, to replace petroleum-based resins. Next, we looked at fiber, made out of plants, right? This is not a new thing necessarily, but the industrialization of plant fiber for the purpose of composite materials. So one thing I'm really encouraged by is this, these emerging technologies, both on the material side, but also on the manufacturing side, to make sustainable materials, composites in particular, for vehicle technology. Now, kind of shifting gears a bit, one of the things I want to talk about is, as we think about these new vehicles and then the new applications, capabilities, I think for me, it's really important. What is the purpose, right? It's got to be more than just the technology, right? What is the purpose? And so there's a book by Rick Warren called The Purpose-Driven Life. So taking on that, I say the purpose-driven design, right? Yes, technology is important, but what's the purpose that we are building it for? And for me, it's really about some things have been brought up before about things like climate change, but also exploration, right? How do we both manage our changing world, our warming world, but also how do we continue to explore our planet and the moon and other places so that we gain better understanding of our world in general, right? So let me begin with first on climate change. And one of the things that I want to bring up is fire. Now, I live in California, but other places like Australia and Canada, we in Europe have been facing increasing fires, right? And really not just fires in the wildland, but fires in the wildland that are next to urban areas. And this has become quite a bit of a problem. So that now at this point, I live in California, so I kind of expect things to be bad, right? That's the way life is right now. And so the people that fight these fires, right, they're just using rakes, shovels, axes, right? And so the question that I have is like, how might ultimate mobility vehicles play a role, right? Given that these hotshot crews are in inaccessible, rough, rugged terrain, what can we do? And if they will be doing more of the firefighting because of climate change, then what could be made to help them do their work better and safer? Shifting gears altogether, almost another extreme is this idea that this need to explore, to understand our world for different reasons, and certainly one topic that's gaining global interest, I would say, is lunar exploration, but also other planets too, but lunar exploration in particular. And really, there's some really interesting findings over the last 30 to 40 years. Is one of that we have discovered water ice on the moon, right? Which can be used for drinking, it can be used for building materials, it can be used for fuel if you're to convert that to oxygen and hydrogen. And of course, the idea of a car on the moon is not new. It's actually 50 years old as of tomorrow, 50th anniversary of Apollo 15, which had the first car on the moon, or lunar roving vehicle, if you like, altogether 3 missions to the moon with the LRV traveling almost 56 miles altogether. So really just thinking about how do we do that even more, not just hundreds or maybe thousands of miles of exploration. So I want to maybe kind of begin to wrap things up here. So as in this idea of reimagining mobility, right? One of the things that I think about with all the advances of technology at large, not just materials, but also automation, et cetera, is what is the future? I think the way I think about vehicles of the future, I call it collaborative mobile autonomy. And this is not a new thing necessarily. It's certainly been in science fiction for in different ways, both serious and funny. This is a picture from a movie, very funny movie, about a companion robot, right? That helps this gentleman. Actually, he helps this gentleman steal jewels, right? So the robot is just doesn't have any moral code. It just helps this person live. But the point is that I think this is coming, right? We have the ability to make and manufacture, right, in an economic way, technology tools that help people live, do jobs better, whether it's exploration, firefighting, or living, hopefully not stealing, right? But doing something useful. So I'm going to close up this talk. I'm going to say thank you. It's been a pleasure. Just giving you a glimpse of what I'm doing at my team. I do that because as a part of context into the bigger picture of where additive will be fitting into, and I do think it will fit into someplace, but there's a bigger picture that is a part of. So I'm looking forward to the panel discussion, and I will turn it over back to the organizers. Thank you very much.
John, thanks very much. Thank you. We wait eagerly on how you will be taking vehicle designs to new heights, incorporating AM. That's something very exciting for us to look forward to. All right, our next speaker is Mr. Stefan Roeding from Additive Flight Solutions, or AFS. AFS specializes in additive manufacturing and provides high-quality additive engineering support and services to various industries, including the automotive. They've been certified AS9100D and they have standards in the provision of engineering as well. AFS provides certification, support, and production of AM part solutions for many industries. As the Deputy General Manager of AFS, Stefan will be sharing today his experience with his presentation on staying ahead with certified applications for transport. Let's welcome Stefan. Stefan, over to you.
Great. Give me a second to just share the right screen. And here we are. Yeah. Thanks, Mahendran. Thanks for the nice words, actually. Let's come straight to the point. AFS is a joint venture between Singapore Airlines Engineering Company and Stratasys. And we started to focus on aviation parts, which means we had to go through a very tough certification process in order to get parts up in the air. Let me start with some news from the market. You heard about our speech from our colleagues from Daimler-Benz, and by sheer coincidence, this is actually one of the first news I want to show, actually, that there are a large number of customers in the automotive and transport sector who are going into additive manufacturing because of their benefits, which means AM is able to provide spare parts, replacement parts, and keeps actually the cost down on storage and location cost. And as you have heard, actually more than 200,000 out of 300,000 parts are not on stock. AM might be a solution, or is a solution for several customers already today, to fill up the gap between having parts on stock and print on purpose. We see a lot of news in the market of a lot of rising numbers. I saw some questions in the panel, actually, and there was one question regarding how much material is really used. And I think, if I remember correctly, in 2016, the whole consumption of metal powder for all worldwide 3D printing machine was on around 600 ton. So this is for someone who's in the industry, actually, and knows, for example, that just a small niche car manufacturer in Germany, Bavaria, he's casting 86,000 tons per year. Then 600 ton in 2016 is nothing. And even if you have an exponential growth, and you are assuming that we have by 2021 consumed metal powder of, let's say, 10,000 ton, we are still far away from playing a real significant role in mass production. But I think we are not there today, and I will bring some more information about that. But other news, and this is actually a very important point where AM is used today, is actually tooling. And here in this example, Ford saves several millions per year actually in 3D or with 3D printing, but not on produced parts, but mainly on tooling. And most of my examples come from tooling today. Another very important point, and this is the last news I want to show here, is that's a very interesting report from the Boston Consulting Group, that there's still a lag today between the 3D printing industry and the end user, the customer who needs to produce the part, or the companies. Simply, a lot of companies are left alone buying a printer, and then actually they have to go through a long journey of pain and spending a lot of money. And I think what is needed in the industry today is more cooperation between the client and the supplier of the additive manufacturing technology. Rather, maybe it's a machine maker, but also a service provider. As a business outlook, and I was quite happy to see the container from Daimler, additive manufacturing clearly became faster. And we have today a much larger base of different materials with a really growing number. You heard our colleagues from Hyundai. there is a constant development on new materials, which make it more interesting for more and more industries. But even today, and that's a very important message, you can put your factory into a container, and it's not a dream, it's happening. You saw the picture from Daimler, it's happening really. And place it where you need it and produce parts where you need them and when you need them. And this is actually the very important message. Today, polymer actually, surprisingly, is still the largest market segment with 3D printing. We see actually that metal, of course, is growing, but still polymer still plays a major role in 3D printed part. The reason why it is much larger, wider available, and the entry level cost is, for example, for an engineering printer, much lower. Finally, it comes to the point, and I think this is the benefit of COVID today, something positive about COVID. We see a lot of interruption in the supply chain. A lot of companies are thinking about moving back production from low-cost countries, from Vietnam and also from China, back into high wages countries. This can only be happen with, first of all, a much larger use or higher use of robotics, but also the way we produce parts can play a vital role. So the development and manufacturing is important of parts that you produce them when and where you need them. AM offers here a very economical solution to produce parts on the spot when you need them. So today, actually, what's in for me, and I think we hopefully want to answer these questions here today. Here are two key messages. We can create a supply chain resilience, produce wherever it is needed at point of care, and of course, produce whenever you need it on demand. And this flexibility can be done with AM. So before we start to produce, I think one of the most important questions you have to answer yourself is, which AM system should I use? There are so many technologies out there: powder bed, thermal fusion, fuse filament fabrication, fuse deposition modeling, and many, many more. All technologies are different. So there is no silver bullet. There's not even one technology which can do it all. And technology like SLS can maybe excel very well in front-facing, customer-facing parts when it's actually a smaller size is required. But maybe it will fail actually as soon as we reach sizes of 400, 500, 600, or even 800 or 900 millimeter. Then we see a much more warpage. So it's important to decide which technologies you want to use. Define what you need. Basically, we see, and I think I mentioned this during some of the video bites actually, very often we are receiving inquiries, please, this is my part, how much it will cost to produce it in AM. And our question will be, or our answer will be, most times it is 10 times, 20 times, doesn't matter how much more times it will be expensive. It is more expensive because the design is meant for conventional manufacturing. So you get the best results when you describe your part before you design it. Describe it, decide what are the main functions it should supply, what are the main requirements on the part, and then decide based on these factors, what is the best technologies we can use. So please start design only after you decided in which manufacturing technology and in which of these many different AM technologies you want to produce a part. Then I can promise you that you will get very cost efficient and economical parts. Today we see four main segments in the industry of 3D printing machines. We have a huge segment of design where the polygets with full color printing and also the SLA printers or SL printers offer a very good service. We offer very accurate parts, but the speed, of course, is tremendously low, and they are not really good for high-end applications. Then you have the engineering segment. In the engineering segment, you find a lot of low-cost printers like MakerBoard and Markforged and Ultimakers and many other manufacturers. These are fantastic if you need to have a sample part in visualization part, you want to have a touch and base model, but they are not repeatable. They are not certified, and it's very difficult to have repeatability and reusability of the components. You have the manufacturing side. The manufacturing are the high-end printers, and the high-end printers, we are now suddenly in a price region of beyond 50, 100,000 US dollar. The FDM technology is can deliver certified aviation parts, flying in the component. AFS by itself has produced more than 6,600 flying components. And with a scrap rate of below 0.35%, which is a fantastic result. But we are still not here at mass production. So newer technologies like DLP or thermal powder bed fusion offer the technology to produce larger quantities, up to 100,000 a year actually. But these technologies are, not switch on and you get the part delivered. You have to invest a lot of time and also money in order to get it done. So key is repeatability and process control. Process control is quite important. It's a good example here. That's a large size format printer we are using here also in Singapore. And it comes with all the necessary process control in order to deliver a part together with the necessary confidence. A repeatable process is very much needed. We need to make sure that not only the first part is ready, it is the second part, the third, and the fourth, and the fifth part. As I said, FDM is not a good product line for having mass production. So here actually, because our quantities are low, we are mainly working on commercial vehicles as well as on aviation. FDM is one of the few technologies which is certified. Traceability, one of the key elements you have to take care. I think traceability of material, where it comes from, when it comes from, is a very important point, especially for the automotive OEM, who needs to have the certification and the assurance that every part fulfills all the same requirements. FDM is one of the possibilities. Testing, higher density in carbon fiber printed component. This is actually one of the advanced engineering materials. And we see here a lot of differences. Everyone claims we are working with carbon fiber, but we see when printing with different equipment, actually a lot of difference in quality, because all the tests are done on tensile bars and they are not representing a 3D printed component with forces tested in every direction. So testing is a very important point in your certification process. Coming over now to end-use parts, some of the examples which are used in the automotive industry. For example, battery housing. These are typical scooter parts, and they are actually starting as a prototype part, the same what also Hyundai actually or similarly has shown. These are made in order to speed up the development process. Tough materials like nylon 6 materials or even nylon 12 carbon fiber offer the good stability and mechanical properties which we need for such prototypes in order to test them really with real people weights. Sample replacement parts like radiator ductings here, this kind of large parts are twinned within 20 hours. Having a design issue, for example, and especially for small, this is for a race car example again, you can react very fast on design changes. With different materials, you can live with the different heat requirements. Other technologies, for example, are much cheaper when it comes to large production at scale. At the end of the day, I think AM will not playing a major role until we will come down to price or cost per part. Here we need to be much better than we are today. And with the help of new technologies and especially with the help of new materials as well, we come very much closer to the cost of injection molding with our technologies. And this will continue. And I believe 5 years down the road, AM will beat injection molding or other conventional manufacturing technologies at special cases, not in general, for sure not. But we will beat with complex design components or combination parts the conventional manufacturing technologies, even for low-end consumer-used business cases. I'm not talking about the rocket science or aircraft development. I'm talking about consumer parts. In the public rail and transport, a lot of the materials today are already certified for public transport, and there are several certifications required, and most of the materials we are using here in Singapore are certified. A good example from the industry is here Siemens Mobility. They are producing the parts on demand, and as you can see from this example here, it's mainly about bumpers. The manufacturing time has been reduced by 95% because they produce on demand when it's required. Another nice example for automotive parts, end-use parts, which are driving, it's a nice example from China here, are full-colored customization. So obviously the price for this customized parts is much higher, but there is no other technology right now which could supply this kind of customization. It is already used in many different OEMs, at different OEMs, different vehicles, from commercial vehicles over also here passenger cars. To me, actually, the largest sector is tooling right now for AM still. As you have seen the example from Ford, they save several millions per year. We have so many opportunities. Every time we go to a customer and we do a so-called factory walk, we identify normally on the spot 20 to 30 applications which we can develop with AM to offer a faster, more economical, or even cheaper solution. So the different areas in the factory floor are assembly, tooling for assembly processes, aided workers to align and hold parts during assembly. Checking fixtures, checking gauges, hand applies, all this kind of quality control checking tools. R&D tooling used in the development phases of product development and manufacturing. We have applications in the quality control department, which means measuring fixtures, holding devices, optical target frame settings, and many more. Packaging logistics. A lot of our applications today are specialized trays for a special assembly stations, where we actually create nice trays in order to supply exactly the right parts to the person who need to assemble a certain sub-assembly. Health and safety. I think there's a very nice example from one of the leading automotive OEMs, where he printed a special glove to support the employees' pushing force of doing the assembly. So a lot can be done for the employees, which is, I think, one of the very important points in order to keep good and qualified workers. And of course, automation and of arm tools. Here, the main benefit comes clearly from weight reduction. So we see the tooling actually in the main benefit in tooling. We are replacing a lot of aluminum tools with 3D printed materials. Much less weight means fast operations. Fast operations lead to a higher profit. That's a very nice example. I have this also with me. You can't see it, unfortunately, due to the screens. Actually, these are window wiper alignment tools made in nylon carbon fiber with a length of 1 meter. The weight reduction is, of course, tremendous, and it leads to a much easier handling. We can go on in all this kind of tooling. It comes down to the same point. You need to start and identify an application, and you need to approach a person actually who has already experience with 3D printing materials and design, because the manufacturing technology AM is different to, for example, layoff tooling. Actually, it is different to milling. It's different to any other technology, and you need to learn the design ready for this kind of application. nice example of a very high end manufacturing, automotive manufacturing end of arm tooling here. Weight saving more than 61%. The cost here is not so important. What is much more interesting is the cycle time increase. By saving more than 20% of your cycle time, the company is able to earn much more revenue per part based on the faster movement of the robots. This is a nice example from another automotive maker. You see the original aluminum weight window assembly tool. Obviously, you have to take special precautions not to damage the vehicle. With a much lighter in polymer printed tool, you can avoid this kind of damages. A little bit about AFS shortly before I come to my end. Actually, we are not only, of course, AS 9001 certified, we are also aerospace certified, and we are working right now on our EASA approval. We are working mainly with Fortus 400, 450 and 900s and DLP printers here now, and concentrating really on high-end materials. We are not looking for prototypes. We are looking more on the serial production or production at scale. Our equipment, our quality equipment, we also spend a lot of money in our qualification equipment, which is required in order to supply everyone with a decent measuring report to prove our traceability and our capabilities. Yeah, we also have a small web shop. You can upload your components in order to order the parts. And here we are. I'm handing over to Mahendran again. Thank you very much. I hope you have seen some interesting cases.
We definitely have. Thanks, Stefan. That was fantastic. In such a short period of time, you managed to paint the full picture and an optimistic view on what AM can do in the transport sector. So great insights and great use cases. Thank you very much, Stefan. Next up, we have our final speaker of the day, Jonathan Meyer. He's the Chief Product Officer of APWORKS, which is a spin-off of Airbus with a mission to apply AM technologies and intellectual property developed by Airbus across a broader industrial scope, including motorsport and automotive. John is responsible for product strategy and implementation. Prior to that, he started his career at Airbus in 2005 and discovered AM early on, thanks to the pioneering work being done at Airbus at that time on the application technology. So he's kind of following on that. He's gone on to work on the A350 program into R&D in 2009 and led the development of applications of metal powder bed fusion technologies. So I shall not, he can go on and on. There's a lot more to say about him. So I'll just hand over the time to him because he's got a lot to share with us. All right, folks, John, take it away.
Thank you very much. So let me just share my presentation. So hopefully everyone can see that. So thanks for the introduction. So as mentioned, I'm John Meyer and I'm the Chief Product Officer at APWORKS. And to give you the background, I mean, firstly, it's important to specify what kind of additive manufacturing we're talking about. And in our case, I'm going to present around powder bed fusion of metals, just to be specific. And the role of APWORKS in that ecosystem is helping customers, including OEMs, to develop better performing products faster using additive. And so we're heavily focused on engineering and also software competencies, as well as production. We think that that combination is what really is essential to deliver good quality additive manufacturing solutions. So when people are talking about additive, we all talk about the benefits, and the benefits are really dependent upon, again, the technology and also the application. So as with many things, you can have a combination of benefits and drawbacks. You normally can't get all the benefits possible at the same time in the same application. And it's really important to understand that. I mean, in this presentation, I'm going to talk a little bit about the benefits that AM can bring in terms of performance, not just product performance, which normally comes through new materials. And often it's surprising to people that some additive manufacturing materials and processes bring better material properties than traditional processes. Also new design capabilities, as others have mentioned before. in terms of topology optimization, weight saving, and so on, but also the performance of an organization in developing a product faster. So there's the performance in terms of a shortened development cycle, and that often lends itself also to product performance, because you have the potential for more iterations through test than if you used a traditional approach where you're always about mitigating risk, because you're about to embed a lot of risk in tooling, for example, and so on. And so there's a tendency to not try things, but rather to not try things in order to mitigate risk. And I think AM will lead us, as we've seen already in, for example, the space sector, to quite rapid innovation, simply because the tool is available to go faster. Agility is a dimension I just talked about in terms of performance, but there's another dimension to the agility brought by additive. And a lot of that is around the fact that it's a toolless manufacturing process. So the printing process itself is toolless. You have a digital workflow. Of course, that lends itself to workflow automation, to distributed production models, as people have mentioned, and also to supply chain service models, simply because it's much easier to merge different products in the same production facility when they don't require physical tool changes and so on to produce. So I think that's another benefit of AM, which is definitely exploitable already today. In order to present this, I decided to pick an example, and I thought I'd actually take the interesting approach of taking an example from around 5 or 6 years ago, where we did this primarily actually as a marketing exercise at the time. The reason being, we were even back then doing lots of projects which involved safety critical structures, topology optimized, etc., but in projects which were under NDA, and there was no way that we could ever show people what was possible with AM. So this became an internal sort of lighthouse project to try and demonstrate what was possible with AM, but also for us to learn from as well and get our engineers hands-on and more involved in a more ambitious project. And so we were quite early, I would say, in using an electric motor on a bike, and that was the development of the Light Rider. There were a few things we put into that project. So one was Scalmalloy, which is a material developed by Airbus, which we were set up to commercialize as part of our mission originally. And that's a very high strength aluminium alloy. So the frame is made of Scalmalloy. That was one of the conditions of the project. Another one was the application of topology optimization to minimize the mass. But really important and not mentioned enough is the coupling of that with design for additive with respect to orientation, support structures, and nesting of parts for printing, and also the post-processing, which people always forget to talk about. These things don't come out of the machine ready to use. There's a lot of post-processing involved. And in those cases, you should be optimizing for the full process chain, not just for printing. In many of the examples we see, people apply topology optimization without thinking about the process chain. And then actually the parts are extremely expensive to produce because they've been basically not designed for any particular process. They've just applied topology optimization. So this example, I'll try and give you a sort of warts and all view and a little bit of a voiceover and tell you what we learned about it and what we've learned to this day, how this has evolved. So firstly on the material, I mean, the main benefit with the Scalmalloy material is the high strength. So you're talking about yield strength, which is in the end what you want to use for most design calculations, is a little bit more than double the yield strength of the more conventional aluminium alloys, which are based on casting alloys. Now, why would we want that strength? I mean, one argument is weight saving. We're making an electric bike, I think was mentioned earlier, range, performance is all related to mass. But actually, also because we're using an additive process, reducing mass means reducing the amount of raw material used and reducing the amount of printing time. And that's essentially reducing the costs of production. A strong caveat to that is the next point, that it depends the total amount of material you use, not just the amount of material and printing time that would be going into that final part if it required no support structures and if it was perfectly nested and orientated. So those other dimensions are really critical, because just designing something for minimum mass does not necessarily mean minimum cost for AM. But when you take account of the production process and optimizing for that as well, then that is the way to achieve a minimum cost of production by AM. So in terms of a sort of conceptual process, I mean, we obviously, everyone has to start with a concept, and we had this funky concept design. What we thought would come out of a topology optimization, sort of an inspired skeletal design. We wanted to show, of course, show off the topology optimization. So the idea was not to put a fairing on it, rather to make it really visible. But then comes the design process. And I think most people are familiar with the idea of, you know, doing a detailed design and stress analysis, and then produce the part. But the critical thing to design to cost is that you're going through the whole process. I mean, nowadays people call this generative design. I think at the time that term hadn't been coined, but it's essentially what we were doing. We had to look at something which didn't fit inside a build chamber. So for those not familiar, with powder bed fusion 5 or 6 years ago, the build chambers were 250 millimeters, 250 millimeters, 300, 320 max was what you could achieve on the Z height. So it was pretty clear that this frame needed to be split up into multiple builds and pieces, and then welded back together to make it work. And we'd done projects like that, again, in real applications where we were welding assemblies. So we knew that one of the keys to making this efficient is obviously to figure out where are the points you should split up this design, such that the printing process is efficient, but also the assembly and welding and fabrication process is efficient. And in this case, it's quite a large structure. There are a lot of welds and there's a lot of builds to be done. And if you take just purely a linear approach, you're going to get an answer. But if you want to get the best answer, you obviously have to iterate a few times through that loop. You know, you learn from errors. And of course, the generative design approach is to look at all those permutations in parallel, basically. So essentially, in this case, we're doing an iterative design to achieve a solution which we believed was a reasonable solution for the technology we had available. Another key point with topology optimization, there's plenty of tools around topology optimization. I mean, we started with this in Airbus many years for AM. One of the advantages we had when coming out of Airbus was knowing how this is done in aerospace for traditional manufacturing technologies, and the fact that you really need not just to do a topology optimization, but to do then a design interpretation, a real sizing loop. So you're adapting the design and the sizing, and all those details, all those stress details need to be considered in the detailed design, like, for example, the weldments, but also any features where you're going to get stress concentrations. And that's not something that comes straight out of any topology optimizer. Tools are getting better, but in general, you have to do an independent finite element loop result and a design interpretation. We have to do the detailed design. We have to look at how those parts then can be nested in the build chamber and what the impact of that is on the support structures, the print time, the material utilization. And as you can see from that picture on the right, it wasn't actually that great. And one of the reasons is that when you have a smaller build chamber, you're compromising heavily your ability to orientate parts. So one of the advantages of bigger build chambers in AM is not just the ability to build bigger parts. It's not about parts that fill the chamber, that's what we should be doing. It's much more that it gives you degrees of freedom in terms of orientation and nesting to get the economics better for smaller parts. And I still think the most efficient production parts with additive are parts that are quite a lot smaller than the available build chamber space, where you can fully exploit nesting and orientation to get an efficient packing and an efficient production time and material utilization. So this is, from that point of view, like a worst case example. We had a huge product, we had to break up into little pieces and trying to shoehorn them into a small chamber. And you can see all the red on the right, that's all support structures. So there was quite a lot of waste when we did this with these small chambers. And again, it's an iterative process. We had to go through loop after loop after loop to check, you know, how we got this right. And there's actually a slightly amusing anecdote to this, which is in one case, we actually got all the way through to production and found we nested the parts so well, they were actually nested in a way where they couldn't be separated. So they weren't touching, but they were interlocked in a way where they were inseparable. I mean, so sometimes those are the memorable mistakes you learn from. But it does show kind of how tricky it is when you end up with these very tightly packed nested builds. Then there's the production. And people often think of this as just, you know, print the part and then you're good to go. The reality, and especially 5 or 6 years ago, the reality was after that, there's a lot of hand finishing. So lots and lots of bench time with bench tools to get the parts from a build plate of parts with lots of support structures to something that's of a reasonable quality to then go for post-processing. Since that time, a lot of work has been done in the last 5 or 6 years on automated finishing. And of course, we utilize those technologies now as much as we can. And maybe this is a little bit a story of where we were and where we are now. But it's interesting to see, looking back, how far the industry has come. Back then, it was all about hand tools. You can see them behind on the workbench. So once we got all of our parts together, a kit, you can see there's a lot of welding to be done there. And that was a nice challenge. But as you can see, we achieved it. We got a nice welded assembly of a good quality. And to give you an idea of the full time frame here, this was basically from the first design, let's say, through to the final product that you'll see at the end was in about 6 months. So that included all of these steps, including design, optimization, printing of all of these parts, and welding, finishing, and assembly. And there you can see the assembly coming together. We obviously, to minimize the amount of work we had to do, we used as much as possible commercial off-the-shelf components and designed the bike to fit those. And that obviously made our lives a little bit easier. There you can see the prototype Light Rider. And in fact, we saw many inquiries from people who wanted to buy one. And then the question would be, well, why didn't we sell loads of these? You know, why didn't we go to market and produce a load of these? And the reality is that the economics 5 or 6 years ago just weren't there. And maybe a little bit more on that later. But what we did have was a working product which we could show off and we could use for the purposes we wanted, and also which gave a huge sense of satisfaction to the team that they developed something that worked and that they could show. You know, so much of the stuff they were doing was under NDA. They couldn't show their friends what they were doing. Really great to have an example that they could show their friends in the world. So maybe my takeaway point, and this is, let's say, the first point with heavy caveat on the next slide. In additive manufacturing, cost is proportional to mass. The caveat being total mass printed and also the impact of what you print on the post-production processes. So the point being, we've seen lots of applications where mass traditionally is irrelevant, where people don't even think about it. Tooling is a prime example, where people tend to take a block and they do as little processing as possible to that to make a tool. However, if you now send that block to a supplier and ask them to additive manufacture it, the price will be eye-watering because you're wasting all that printing time and all that material on doing something that you don't need to do, putting all that extra material there. Minimizing mass is minimizing cost. They're proportional additive manufacturing. And there's a lot of industries where they need to really embrace that to get to that point where they find the right applications for additive. And that's something I really strongly believe in. And the other point, and I think Stefan made it really well earlier, is you need to design for a specific process chain, not just say, here's my CAD model, please print it. The reality is you only get design to cost when you go for the full process chain. And my last slide, which is, let's say, a takeaway and a view to the future, is back in 2015, what we were dealing with and where we are today. Now, with the smaller build chambers we actually had to do 12 builds to produce that frame. And that maybe immediately gives you an idea why that wasn't really a viable prospect for us to produce that product. Even as a niche product, that was a heavy production process. Today, it's 2 builds. 700 hours to 160 hours for production. Still, not necessarily a low cost route, let's say for a bike, but for a very niche product, it starts to become in the range of viability. And the key point with the technology is the trajectory it's going. That's 5 or 6 years. There's a trajectory the technology is taking. And in the post-processing, there's also been a huge improvement. You can see the effect on the number of welds, but there's also the effect on post-processing of the parts through automation, mass finishing processes being applied, and so on. So that's all I wanted to share, really, but it's to give you a view on the importance of design for AM, and also the fact that sometimes we're shooting a little bit ahead of the curve, but we've got to make sure we learn from it, and then that we're ready to capitalize on it when the timing is right. And I think we're getting there with metal additives today. And certainly there are lots and lots of applications now which are not too different from this, which
John, thank you. Thank you very much, John, for sharing with us on the value of engineering in metal additive manufacturing. Very inspiring. And yes, and then you showed with your example how things are actually getting better. You know, the costs are coming down and the time to build is also getting faster. So great job. Yeah, so we are now down to our final segment of the summit. Stick around as we invite our speakers back onto stage for a live panel discussion. If you still have some questions that are pressing on your mind, just please drop them in the Q&A box below. But if not, we will now welcome back the moderator for this session, Joris Spiels. Joris, after hearing what the speakers have had to say, I'm sure you're ready and pretty much inspired to lead today's discussion. So I shall not delay you any further. So take it away, Joris. The panel is all yours.
Yeah, thank you very much. Thank you. Yeah, I thought it was a really great series of discussions and things there. We were learning a lot of very practical information. I think anytime we're getting a lot more practical, we get a lot more kind of real. I mean, we start talking about real examples and we start talking about real stuff that's happening. And I think a lot of the times the 3D printing hasn't been mature enough. And also a lot of times 3D printing has been kind of a lot of people can't share a lot of information. So it's nice to be able to talk a little bit more broadly and more openly about real stuff that's going on. So we've got a whole bunch of questions at the moment. I'd like to start with a question for everyone. I mean, I think the first is like, so, you know, we've talked a lot about the opportunities for additive, and we've also kind of, some of you guys have also mentioned the limitations. And some of you say, hey, it's about design. Other people think it's much more about materials and things like that. So what are the things that we could do to really advance additive, in specifically in automotive and transport? I like to just ask that generally to everyone. So guys, like, you know, what are the really major roadblocks that we really must tackle to make this technology for a lot of different applications?
So one of the things I've seen is the design tools are not necessarily as suitable. The CAD tools in particular, I'd say that some of them are incorporating manufacturing information and materials information, but I would suppose, except for perhaps metal, as the polymer and plastics and composites, there's lacking of the data on the material properties and the manufacturing to begin to think about, because as mentioned before, the design phase, right, is really critical. So those software tools really help designers, engineers in the design phase, conceptual design phase in particular, to think about the materials and processes for additive. It just seems to be lacking. I think the workaround has been doing a more complicated workflow across different software packages, but then that gets to be very custom, I think. And so I think that's been one thing we've seen so far. I know things are always changing, but that's the issue that we've come into in our experiences.
Other people like to comment on the same thing, or? But okay, so just generally, I mean, I think a lot of things are really exciting. I think one thing, we are all focusing on very small parts, right? So small parts because additive is expensive. But we do have other technologies like DED type technologies, like laser welding type technologies that are capable of making larger components. not a lot of attention's going there, but we could theoretically make like a chassis-sized 3D printed part. Are you guys looking at those types of technologies? Are you excited about those or not really?
If I could jump in really quickly on, and that leads maybe another comment is like even just being aware of those options, and you have to be aware of those options in the first place to even begin to explore, right? So it's not like we wouldn't be thinking, wouldn't be open to it, but it's like you have to kind of do the homework first, right? And so there's a lot of effort to even get yourself acclimated to what's possible, right? And then you can think about it. So that's been a little bit of an obstacle. We do a lot of homework and find what's going on in the industry, and then you can start designing, right?
Yeah.
But I have an answer to this. My colleagues at Deutsche Bahn already did have an in-depth look at these processes as well. For example, the secondary roll stop of the ICE high-speed train I showed in my presentation was manufactured with a DED process. Concretely, it was the WAM process, so wire arc additive manufacturing, and it wouldn't have been economically feasible at all, or at least I don't think manufacturable in a powder bed process. For example, this is a 30-kilo heavy part, and also for tooling, we have quite seen some applications. For example, for tooling of fiber placement, so manufacturing of composites. Many tools in this field have to be reused and reused over a long series, and they have to be out of metal. So they also experience some quite of thermal stress in the autoclave, and their the manufactured tool is ideal and is economically feasible in many ways.
Yeah, definitely. I think we have another question from someone in the audience. That's also for you. So we can jump right in that. Do you need to be? So the question was about certification testing of these parts and how do you ensure consistency of parts specifically for rail? Especially in rail, it's very difficult. Parts sometimes have to last a decade or several decades or more. So I can imagine that's very difficult.
Yes, rail is a heavily regulated industry, like aerospace as well, and the authorities are very very concerned about the quality of the parts, especially when you change the manufacturing technology of an original part, which has been conventionally manufactured. In this example I've showed, my colleagues at Deutsche Bahn had to do extensive testing, really extensive. So not only do a very in-depth reverse engineering, but also do all of the analysis tools, destructive and non-destructive, put it in a shaker, put it do a CT scan. All these steps had to be made, and that was more the economical bottleneck than the manufacturing itself, actually. And that is also a big field where we have to develop further to have more methods to do all these assessments, but in a more economically feasible way.
Yeah. Oh, definitely. I think it's a good point. I mean, it's very difficult. I mean, we're producing parts in a different way along the powder bed, fusion bed, for example, with different kinetics and stuff. So, each part is unique. I'm actually of the opinion we should actually individually Q&A every single part, which some people don't agree with, or most people don't agree with.
For parts which are not that safety relevant, lighter QC measures are absolutely okay, but on safety relevant parts, testing gets really extensive and expensive as well.
Definitely.
But there are, of course, sweet spots in the industry, actually, especially when it comes to public transportations, there are different classifications formalized, actually, and not all of them require even certified material. If you go to an exterior part below 100 grams, for example, then you have the lowest demand in polymer, for example. It's so it really depends on the application. Again, the application determines the technology you're using. And as the example from Deutsche Bahn, obviously, powder bed SLS is far too slow for such a process actually to create such a big component. So you need to use other technologies. And as I said, this is the first and most important decisions you have to take. Decide on the technology before you design, and then go ahead.
Yeah, definitely. And we've got questions for the Daimler team, if you will, for either one of you guys, if you want. So you guys mentioned digital rights management in your and the business model of a decentralized production. So, what's the importance of a digital warehouse in this, and what's the importance of these elements in digital production?
Yeah, Daniel, if it's okay, I will answer this question. Sure. Yeah. So yeah, a very good and interesting question, in my opinion. So I think the setup of our digital storage forms the basis for all of the different digital business models we're involved in. So for example, the setup of a digital rights management and also the setup of a decentralized production. And for this digital business models, it's essential to generate the necessary database that includes all different parameters that are relevant for 3D printing. So for example, using the right material, using the right layer thickness, using the right orientation of the part in the building job, and then to store this data in our digital storage, to have the necessary database available, and then to be able to produce the part on demand and as quickly as possible, and of course with the right quality at one of our 3D printers wherever in the world. And for this different digital business models, the digital storage is laying the foundation, I think. Yeah.
Yeah, definitely. And there's another question for you. I think, what's the role of the Center of Competence 3D printing within Daimler AG, and what are you doing to expand your 3D printing activities? And how do you plan to grow within Daimler? How do you plan to extend these activities across the company?
Our role within Daimler AG is to coordinate and consolidate all the 3D printing activities, to get all the stakeholders together on one table and talk about the technology, because in our opinion, it could only be successful if you take everybody who is affected on the same table and discuss topics and issues about 3D printing. And we want to expand our topic with implementing our business model to other business units, and of course also to external customers, as Janis mentioned in his presentation.
Yeah. Okay. So that'll be very interesting. You can get a part made for you by Daimler at one point. So your own Daimler part. You used to be able to get Airbus to make parts for you as well. So about Stefan, like, what's the role? I mean, I think you mentioned that you guys are going for a bunch of standards and different standards for your company to try. And what is the role, like, on the one hand, we've got emerging standards for 3D printing. On the other hand, you just use the regular ISO standards that are normal. So and there's many more emerging new standards coming on board. So what's the role of standardization for you guys in additive, especially in the area that you guys work in transportation?
I think it is quite important to, first of all, fulfill the bare minimum of an ISO 9001. I think there are too many, suppliers out there who are not following a simple standardization of processes actually, and the ISO is helping you to implement this standardization. If you're going then along the road and you want to be certified for AM, then there are now several programs available from certification bodies like TÜV Süd, for example. They offer very special certifications which are dedicated for AM processes, like the DIN 17071. Because our focus was more on the aviation, of course, we are looking for the highest possible standard, which is EASA or FAA standards. But of course, with this kind of certifications, a lot of costs are also involved. For sample printing, for rigorous testing, you have to invest in a lot of quality control equipment. And only if you're willing to spend this kind of efforts and of course also money, then you are prepared for real serial and manufacturing purposes actually. I think we want to differentiate in our case us from a figurine printer actually, or prototype printer. If you want to produce serial parts or mass production or serial mass production, you do need to have certain processes in place. And this you can only do with the established certification bodies, actually. So to me, actually, it's the base foundation of every good manufacturing process.
Totally. And Jonathan, I think also you guys are also very interested in the serial production and things like that. And you talked a little bit about some real roadblocks and some real things you're trying to solve. I think it's really interesting that you guys are looking, of course, at Scalmalloy. Like we'll go one very specific question is what's the fatigue strength of Scalmalloy compared to regular or different aluminums? Which of course I think very different. Yeah, exactly.
Yeah, but it's in the range. Like if you take a 70-75 was type alloy, it's in that sort of range.
Yeah. So given your experience with trying to get Scalmalloy to production, I think it's interesting you pointed out that we can reduce the mass in the printer and we can have a less printer hour, but we may actually have like more post-processing kind of things. Are you guys designing for post-processing? Are you guys, when do you take post-processing into account? Because like you said, like with this one example where you kind of got stuck and you couldn't unstick a part. So when do you have to, as a designer, if you want to do design for manufacturing, when do you have to take into account post-processing?
To be honest, I would describe the design process, and it's probably true of every manufacturing technology. Good design involves starting at the end, what you want to achieve, and then working out all the manufacturing processes you're going to need to get there. And then you're designing according to that. And I think the only reason we, and I say we as in the world, have fallen out of habit of doing that is because we've become so familiar with rules of thumb regarding how traditional manufacturing works. It's kind of easier not to bother doing that, not to have to think about it. Just go, well, if I always do this, it always works, you know? And you get the grumbles from the manufacturing engineers that it's not that efficient, but okay, or you need to change this or change that. With the new technology AM, we have to stop. And I hear it so often, can you just send me a one-page design rules, right? And then I'll just have to talk to you, right? And the point is, you need first to establish a mental model in your head of how that whole production process works. Then you can design for it. If you don't have an adequate mental model in your head, no cheat sheet is going to help you design for process. And that's just a fact. So I think it's really important. And the best designs that we've done for AM with customers have almost zero support structure. I'm talking about what is necessary to attach it to the platform that has to basically disappear. But that's about it. And that makes a huge difference, not just to the process economics, but don't forget what I told you about support removal and all those post-processing costs. As soon as you've got services that aren't touched by support, your post-processing costs reduce dramatically. And I think that's the only way to push the economics of the process is to really focus on that.
Okay. Because we got another question, which is, if the technology continued to develop as expected, what do you think would be the limit of the volume crossover economics of 3D printing technologies compared to alternatives such as casting?
I could give you like the difficult answer being depends, right? Depends on the depends on the, which is just like, I mean, that's a cop-out answer. But the question I would say that will drive it all is, you know, what are we competing against in terms of volume economics? What we have is a piece part production cost, which is higher. And we have a non-recurring cost, which is lower because we don't need physical tooling and we're automating. We're just becoming digitized quicker than everyone else, right? In terms of how we get to that product. So you need to divide that piece part, you know, you need to divide that NRC across all the piece parts. So you can see that if you're making 1 million piece parts, that NRC can be huge and it makes almost no difference, right? In the grand scheme of things. It's why the volume economics work at the low end today. That volume economics is going to creep up, but remember, dividing by that volume. So I personally think until we get cycle times of seconds, measured in seconds rather than hours, I think it's going to be limited to the less than 10,000 units. You know, the bit that normally is not on the log scale. At least for most applications, the exception to the rule is complex stuff, where actually you're talking about simple ops, you know, where you're just injection molding or casting a one piece. As soon as you have assembly operations or fabrication and you can do part consolidation, that changes that story dramatically, right? And that's where the volume economics already work better and will continue to work better. As long as you're talking a one-shot manufacturing process today, like casting or injection molding, you're going to really struggle to break out of the low volume end, I think.
I think it's interesting about this economics. You pointed out that larger builds will actually allow us to improve things by actually fitting things in more efficiently. And I noticed this as well, because what we were doing is by planning, we were used to plan builds over several weeks, for example. And then we could also fit in more things more efficiently because you had more volume on aggregate. And do you think that's a role as well, that if 3D printing production increases across like a large firm, that they're going to reap more rewards from these kinds of advantages as well?
Definitely. I also think it's more critical for certain types of technology than others. Again, why we have to be specific what we're talking about. As soon as you get into things like binder jetting or selective laser sintering, for example, where a lot of the process time is layer time and not much is added by what you're melting, the process economics are so heavily driven by nesting, by the ability to nest lots, that's where that becomes super, super critical. The other end of the spectrum, like directed energy deposition, like you mentioned earlier, like WAM and things like that, actually in that case, it's all about deposition time, right? There isn't really a nesting effect as such. So again, why we have to be specific what we're talking about, Ferraris versus, freighters. It's different ends of the spectrum.
Yeah, no, definitely. I totally agree. I think it's going to be very interesting to see how this plays out and how the economics work out. How have you been able to sell this to companies? Because we're always more expensive, right? And then is it usually you either sell the dream of AM or you have some perceived benefit? And what's worked for you?
You've got to focus on what actually works today, right? So there's the dream of AM, which is great to project a vision, and we all know that it's going on a track, right? But if you want to actually apply it right now, there needs to be a value for the customer that exceeds the cost of production. So you just have to be realistic. And in general, that means short series production, because the value there is taking out the NRC, agility, the ability to do it really, really fast, get design changes implemented really fast. Those kind of things are the things that do work right now. And the other one is product performance. There are a number of things we do where it's really about making a better performing product that the market wants, and the costs are within the envelope of what the market is willing to pay. And that's the point. If the costs are higher than the value today, they might reach that point in 5 years' time. So we're not going to say it's impossible. We're not going to say AM doesn't work for that, because it's not a steady state thing. But it's more that you got to tackle what you can do right now and then kind of prepare for the future. That's the point.
Yeah, cool. I totally agree. I think for also another question then for the Daimler team, like in a company like Daimler, which is a very large organization with a lot of different things going on for it at any one time, what are the business drivers here to adopt the technology? I mean, you talk about how you want to do it and the digital warehousing and stuff, but what's the logic behind it? Do you want to save money in the long run? Because a company like Daimler has billions of dollars in spare parts at any one time. There's a lot of cash flow you could throw up. Is that kind of the driver, or is it just like you said, like more agility and more iterations and more rapidity in making things?
It actually depends on the issues we want to solve. Most of the time, of course, it's to save money for tooling, for example, at the end of life cycle of injected molded parts, for example. On the other hand, we often have issues in delivery performance, go-to-market times, for example. Topics like securing spare part delivery over the life cycle, when you think about old buses, for example, to receive a better market share. Yeah, these are the main topics, to be honest. Yeah.
No,
yeah, and if I can add something, so I think minimum at the equal important is also the topic to generate an added value for our customers. So of course, with 3D printing, we have the possibility, for example, to shortening, to have a shorter delivery time and shortening of our supply chains. So I think on the one hand, it's very important to use the benefits of 3D printing for us as a company to reduce costs. But on the other hand, at minimum equal important is the topic to generate added value for the customer. And here, I think with 3D printing, we have for both different sides, we have really great potential by using additive manufacturing for us in the bus section.
Yeah, I mean, that's totally good. And then also like we have a very specific question. Oh, sorry. Yeah.
I would add to this. You shouldn't forget the sustainable effects of this, because when you replace a physical storage by a digital storage, you don't need to produce the parts when on prospect, and don't need to hold these in your storage, and many of them aren't needed in the lifetime of the product. Especially also in rail maintenance, there are a lot of old vehicles and infrastructure, and there are many spare parts. All the railway companies have millions of spare parts lying around, and they have a very small turnaround, and many of them are disposed at the end of the service life of these vehicles. And if you could replace at least 10 or 20% of these, there are not only monetary gains, but also in the sustainability.
We got a question.
I can totally agree this point from our side. So by only producing the amount of parts that are really needed with 3D printing, we can really add an important contribution to the protection of resources, and as well we can significantly reduce the warehousing and scrapping costs. So like Helge already mentioned, we can really totally agree from our side about this environmental issue.
Totally. I do think that it's really misunderstood how much capital this will free up as well, and just how advantageous it will be as well in a financial sense, as well as for the environment. We have a specific question for Daimler about this topic, and then somebody wants to know how many metal parts that you guys produce per year using powder bed fusion. I don't know if you are willing to disclose that, or if you're able even to disclose that. Maybe you're not. Do you guys know how many parts you make about, or?
Yes. Please understand that I can't share any special numbers, but I can say that's a low 3-digit volume per year. It depends, of course, on the parts and on the market situation, and on the focus of our daily business. Yeah.
Okay, cool. And then there's something that for Helge as well, because like that kind of goes to what he said, is like, somebody wants to know is like, how can the identification of IAM use cases be improved? Because you are talking about, let's identify these parts and make them, but how do we actually make that more accurate? Because right now, the best thing I've done ever is just say to people, what's your most expensive part? Just go from the list of the most expensive part, and then less than 20 by 20 by 20 centimeters. Let's go. And then that's worked for me. But I don't know, for other people, is there any kind of like, stuff that works for improving that identification of those parts?
Yeah, there's lots of methods around. Some creativity methods, also part screening from the lists of warehouses. But from our experiences, at least in maintenance, this doesn't work optimally. Our experience and experiences from our members are in the maintenance field, at least, that the bottom-up approach is very good, especially in tooling cases, that you broaden the knowledge of AM and all the possibilities within all the maintenance staff, and they come up with the great ideas, and you should collect them and see what really works.
Yeah, exactly. And also it's interesting to note as well that nearly all the top-down approaches have failed, except for like Stryker and a few other companies, but nearly all the CEO says that we're going to do it has gone nowhere. And what I think is also an alternative is what I call the ski tractor approach, where you have a very limited, you're a tractor company, and you make like a ski tractor, right? It's a very limited project to make a very small, low run, low risk for the organization kind of test of doing this. So it's another way that has kind of worked for as well. So some questions for John at the moment. Like first off, like for you, John, what are the business drivers? I mean, it's clear that you're really inspired by this technology and it gives you a lot of things, but for your company, what are the business drivers for really adopting AM?
For me, it's a lot of it has to do with how do we shift the curve of manufacturing into, especially when we get into lower volumes, I think the automotive industry at large is done a really good job of doing high quality, in the hundreds of thousands of units, at a given plant. But when you get down to low volumes, which are under 100,000 units per year per model, is considered low volume by automotive industry, and so we're not as good in making the same part / quality costs at that level. And if you go even further into the tens of thousands, several tens of thousands, that's really in that very, very frontier area in terms of manufacturing. We have the same token. What's interesting is we move into aviation. That's considered high volume for aviation, right? At 10,000, 20,000, 30,000 units per year is massive volume for aviation industry, but for automotive, it's niche. And so we have to bridge the gap there in a way to how do we get quality and costs at low volumes for automotive, high volumes for aviation. And as has been discussed, right, there's a lot of advantages here, tooling and so on. And so I think that's the driver, right? How do we get to profitability at the 10,000, 20,000, 30,000 units, right? It's easy to make an expensive car at low volume. It's hard to make a cheap car at low volume at great quality, right? It's really hard, right? And that's the business driver for us.
Yeah, and is that something, because like we were seeing, like there's an explosion in car models, right? And a lot of cars are basically one big mass customization effort. Like you might actually have a unique car, right? Theoretically, there could be a configuration of options that only you have, even though there's 5 million of these on the road. Right, is that driving this? And do you expect that to continue, or?
I don't see mass customization happening, and the reason why I don't see it happening. So I don't think it'll ever happen, honestly. And here's why. Because if I were to ask you what are the 2 most popular colors in the world for a car? It's black and gray.
Yeah.
Maybe white. White. Is that mass customization? No, it's mass combination, right? And so from a design viewpoint, people tend to, right? It's quite an interesting social / psychological phenomena. We don't tend to do customization, right? There is customization, but it's a niche industry. It's SEMA. There's a big event in the United States, SEMA, right? But it's not. It doesn't. The economics don't work out for anybody, right? Now that you might say, well, if there was another manufacturing technology, then that would change. Maybe, right? But color being the signal for me, it's like, we don't really want mass customization. We just want something that everybody likes, right? We want something that other people will appreciate, something that's good, right? So I don't see it happening, actually.
Okay, I think that's really interesting. You said everyone's always been super positive about mass customization, and I tried for years to get mass customization projects to happen. And you could do a conference really easily, and everybody would attend your conference and stuff. And then you'd want to do a project, and then nobody would actually do the project.
And it's sort of like shirt colors. There's different colors, but we'll like 4 of us are wearing blue. Like I'm wearing blue, right? So is it really? Do we want mass customization? Not really. We just want something that works for us, right? But it's not really mass customization, right?
Okay. I think it's nice to be a skeptic on this, because there's so many people positive, but there's so little that's actually happening. So
I don't think it'll happen.
Okay, that's really interesting. Nice thing to go on the record about as well, right? But
I think it's.
Yeah.
Sorry, I just want to say, John, that's a really interesting point, because that's customization through choice. It's like Henry Ford only got it slightly wrong, right? It's like if he had
he was off by 2 colors. He was off by 2 colors, white and gray, right?
And that's enough. But I think
pretty good prediction, right?
the key with customization, I think, is it's about want versus need. So I think in scenarios where it seems to work, it's like medical, where it's necessity, like what the person wants is an implant that fits, right? What the surgeon needs. Then it works because it addresses a need. But when it's just want, like you say, we're creatures of, let's say, social creatures, and we tend to sort of choose the same things. It's a cultural thing.
Yeah, I mean, I think we also have this thing.
That's a good point. Yeah.
Yeah, we've done a lot of. I've done a lot of studies in this, and consumers also have this what I call a blank canvas problem. It's they look at this thing and they're like intimidated. They're literally intimidated by all the options, and not only paradox of choice, but they're actually being forced to create in a new medium, and they kind of feel very kind of like that they'll be judged on that. So there is like literally I've done studies and stuff, and like we've done focus groups and stuff where this kind of people like, do I have to, you know? So that's actually kind of very interesting. But I do agree. I think, you know, if I could just get 3D scanned the Hyundai lot, and then I get a better seat, that kind of like mass customization stuff, that to me would be, I think, very exciting if you could just upsell people. Because for a car company, I mean, you know, isn't there always like you know, any excuse to give someone to give a person to spend more on your car? Kind of isn't that, you know, shouldn't that be like driving your thinking? Like, because they're going to buy it anyway, why not sell them extra mass customized stuff? Or
I really don't like that idea at all. I mean, like it's like, why? It's like it's so you know, just sell them what they, you know, why you know, why try, you know, it just seems like a trick, you know, just provide good product, good quality at good price, right? Don't do this like, hey, get this little thing here. And I'm like, that's really cheap in my view. I really hate that as a consumer and also a person in the automotive industry. Just do a good job, do it right, and just do it at a good price, a high quality, right? Don't make people get extra for something else, right? It just bugs the heck out of me, actually.
Okay. That's actually really interesting. Don't ever buy a Volkswagen.
I think Jonathan broke the thing down pretty well, because when it comes to mass customization, it is a want versus need. And when you look at the medical field, it often is a need, indeed. For example, there's the leading German hearing aid company, Kind. They do mass customization for the inserts for the hearing aids as a serial process since years. And this is not a nice to have. It's actually needed. And this replaced the crafted inserts they did before by hand.
Oh, exactly. I think these kind of cases, they layer multiple benefits, right? There's a benefit to the end user, right? Which I think the Janis mentioned as well, like, hey, the end user needs to benefit as well from this thing. It's cheaper. And in process, this kind of mass customization is easier to do. If we look at orthopedics, there's even more benefits because we can change the modulus of the orthopedic implant to match that of bone, and we can do wicking effects and stuff like that. So there's a layering of, and those are the best business cases, because otherwise we're just going to be expensive. I'm a little bit curious to the guys at Daimler. Are you guys as skeptical about mass customization as well? Or are you more into this or more open to trying it out? Just because we did broach the subject of mass customization.
Due to the fact that,
yeah, sorry, please carry on, Daniel.
Yeah, thanks. Due to the fact that we sell a quite a big product with the buses, which always needs to be amended to the customers, we are interested in mass customization, and we already do have some approaches, of course. Yeah, and this is our business model since, I don't know, years, to make nearly everything possible the customer wants in his buses. Yeah.
Yeah, okay. So it's a very different way to approach this. I think it's really interesting because we always see it as a universal good. It's kind of interesting that people would look at this as maybe something to be skeptical about or not to be encouraged.
So Joris, maybe a closing remark. We are running a little bit short on time. No,
it's good. I mean, I really enjoyed this discussion. I thought it was nice, everyone to kind of like be so open and so forward and talking about this. And I think the golden age of 3D printing in transport is very definitely happening. There's 3 companies that are making in excess of 100,000 parts a year with 3D printing at the moment. Tens of thousands of end-use parts on cars. And it used to be just, you know, the Veyron dashboard, let's say, and then it was the front parking sensor, which nobody wanted. And now we're getting much more into more serial parts, larger volume, larger production runs. So very, very exciting time to be doing this. And thanks everyone for attending. And thank you so much for being on this panel, guys. I really enjoyed this.
Thanks, John. Thanks, Joris. Thanks, the rest of the panelists. I hate to break this up. I think it's a fantastic conversation that's ongoing. 2 hours have just gone by very quickly. So, so I must thank all of you for patiently being with us for this afternoon and joining us. It's really been my utmost pleasure to have all of you with us today. And I hope that you had a great time listening in and understanding the use of AM technologies in the transport sector. I hope it somehow has inspired you to take a step towards innovating with AM. So I'd like to thank all of our speakers for taking the time in different time zones, late at night, early in the morning, to be here with us in this second installment of the NAMIC Virtual Summit 2021. So the second half of this year is going to be even more exciting for us as we prepare for the largest annual event that NAMIC puts together, the Global Additive Manufacturing Summit 2021, as well as other key events coming to you. So please pay a visit to our events page via this link, namic.sg events, to keep yourself updated and for any general inquiries that you may have. I've had a great time today talking to you and presenting this summit to you, and along with Joris and the rest of the panelists. So from the rest of our team here at NAMIC, thank you very much for being here. So have a great afternoon and the rest of the week ahead. Bye for now.